Okay, so we're talking about nuclear decay. All right. So I want to go further down into this, drill down further into this concept of nuclear decay, and talk about the different types of nuclear decay, particles and energy. And I say both because there's some crossover here. All right. If we get into the really high-end discussion of nuclear decay and nuclear radiation, after a while, there isn't a lot of difference between nuclear particles and nuclear energy. But just for high school chemistry, we try to differentiate on a little bit not so deep scale. Okay? So we're going to talk about what we, in high school anyway, call nuclear particles first, and then talk about nuclear energy as part of decay, a form of energy that's part of the it's a nuclear process or decay process or radiation process. Okay. Now, so of the particles then that we can get out of the nucleus, nuclear particles, I want to first talk about alpha. So, you can keep on the same page you had previously because it's continuing the same thought process. We just stopped to do the cloud chamber lab, okay? Because it's all tied together. All right. All right. Alpha. Now remember, you have alpha decay, then alpha emission, then alpha radiation, right? Well, remember we talked about that. This is the way radiation works. You got decay, which is kind of the breaking down of the nuclear particles or whatever. Then when it spits it out, you get emission. And when it comes out of the atom, you kind of call it radiation. Okay? So alpha is a form of decay, emission, radiation. Okay? And alpha decay, emission, radiation comes from these alpha particles that come from the nucleus. All we're talking about right now today is nuclear stuff. Okay? Nuclear stuff. Yes? Yes, you can. But I want to answer it in just a second, and I'm going to get to it very shortly. Okay? So, what you saw in the cloud chamber was evidence of alpha radiation, alpha decay, alpha particles. Okay? Your cloud chamber showed you evidence of that. Now, if you were looking really, really carefully, and you differentiated between the types of vapor trails you saw, some looked a little different than others. Every once in a while, you saw a different looking vapor trail. Okay? So there were two types of particles that you could have seen evidence of in those cloud chambers. And we'll talk about those in a second. Now let's talk about what an alpha particle is first. Okay? For all practical purposes, the structure of an alpha particle, that doesn't mean it's the same thing now, but the structure, what it's made of an alpha particle is the same as that of the nucleus of a helium atom. Okay, so the structure of the nucleus of a helium atom, not the whole atom, but the structure of an alpha particle is the same as that. The difference is helium atoms don't come out of the nucleus. Alpha particles do. You got that? So where it comes from is important here. If it comes out of the nucleus, alpha particle. If it's a standalone atom with same structure but having electrons too, then it's a helium atom. Okay? Different things. Helium atom. H-E-L-I-U-M. Helium atom. Okay? Both of these have 2 protons and 2 neutrons. An alpha particle in terms of radiation particles, is the largest, but the least dangerous. In terms of radiation particles, the alpha particle is the largest and the least dangerous. Radiation particles. Remember, we're talking about decay, emission, radiation, right? Okay. So these are the particles are the thing that makes the emission and radiation. The particles are what's coming out. The decay is occurring because these particles are breaking out. The emission is when they leave. Radiation is when they leave the atom or the whole structure of the material. Okay? It's the biggest but least dangerous. That's why when we're doing the cloud chamber, you've got to be careful to make sure your uranium ore sample is dry. The alpha particle is so weak in terms of what it can do that if your uranium ore sample is wet, it won't even come out of the wet stuff. An alpha particle will not even, radiation you think of being really dangerous, right? Alpha particles won't even penetrate a piece of paper. It won't even go through this piece of paper. Okay? And that's why somebody asked, it disappears. What happened to it? I was asked that question. Because it doesn't go very far, because even the cloud chamber, even the vapor of the ethanol vapor in the cloud chamber is enough to basically stop it from moving after 5 centimeters, 4 centimeters, something like that. It's gone, right? It's because it stops moving. It's still in there, just kind of floating around. It might be stuck in one of the droplets of alcohol vapor. So what's happening? So this is the alpha particle then is flying through there, and you see a kind of a vapor trail, looks something like this, and then it just kind of tails off and disappears out here on the end, right? Yes? Is that a reasonable cartoon drawing of our vapor trail? Mm-hmm. And so that's what an alpha particle trail looks like. And sometimes it looks a little fatter and sometimes a little thinner, but it kind of flies out there and it's gone. Skinny comet, okay? Only a comet has 2 tails. Okay, let's don't get into that right now, okay? All right, now why does it form a vapor trail? Well, first of all, there is a cloud inside your chamber, but the strange thing in terms of how we think about clouds is that you can't see an ethanol cloud.
When you say vapor, do you mean water or?
No, this is ethanol vapor.
Oh.
You can't see ethanol vapor. All right? You shine that flashlight through there and it looks like it's empty. Clear, right? Yes? But, no. The ethanol cloud, the particles or the droplets of the ethanol cloud, because any cloud is a collection of particles. It's liquid that's in tiny little droplets. Okay? So the clouds we see at night or in the daytime, or the fog we see, are little tiny droplets of water. There are bunches of those water molecules all stuck together. Well, the ethanol cloud is the same way, but an ethanol cloud has really small droplets, so small that you can't see them. But if you push them together, you'll get droplets that are big enough for the light to bounce off. And that's what happens when the alpha particle goes through. It pushes those droplets of ethanol together to make particles that are big enough to see, but only for a second, and they're gone. All right? That makes sense? So it's evidence of alpha particles, but not proof. All right? Just evidence of. There's no proof in science anyway. There's proof supporting something, but no proof of. Okay? There's proofs, but no proving in science. Okay? We don't prove things in science. We offer proofs of it. All right? Evidence. Circumstantial evidence. Okay? All right. So it's made of 2 protons and 2 neutrons. So what do we call atomic mass? Where do we get atomic mass from? What's it made up of? Protons and neutrons. So if I have 2 protons and 2 neutrons, you already know the mass of an alpha particle. 4. You got that? All right. Let me give you the symbol for an alpha particle. This is the lowercase Greek letter A. And it looks kind of like an A. Well, let's see. Here's an A, right? There's an A. But an alpha particle has that on it. There's alpha. You see the difference? A, alpha. Well, kind of like O and C connected, sure. Okay?
Is alpha for alpha particle?
Well, this is the Greek letter alpha, and that's a symbol we use for an alpha particle. Now, if we were just going to say alpha, that's all we'd write. But to do the math for nuclear equations, we need some other information. Now, somebody who does this all the time, they just have it in their head. But I want to give you some training wheels, okay, for doing nuclear equations and getting them right every time. And so this is a perfectly acceptable way to do it, but I'm helping you get it. We're always writing our nuclear symbols with this other stuff on there to help you with the equation. You got that? So what I want to do for a nuclear symbol, in fact, I tell you what, since I'm going to write some other nuclear symbols, I'm going to slide down to the bottom and put all of our nuclear symbols kind of in one group here. Whoop, SYM, POLS, nuclear symbols. Okay, that's supposed to be an M right there, sorry. So, alpha's our Greek letter A with a little loop on the top. Okay, a little swoosh. Alright. But our mass always goes upper left. The atomic mass or nuclear mass always goes upper left. So that means I put 4 right here because the alpha particle has a mass, an atomic mass of 4 AMUs, or atomic mass units. Okay? A nuclear symbol also has the number of protons. Well, how many protons in an alpha particle? 2. And that goes lower left. So that's our symbol, our nuclear symbol for an alpha particle. Got that? Now, if I were writing a nuclear symbol for a helium atom, there's our symbol for helium. How many protons does a helium have? Helium? Yeah, I gave you this tool yesterday. 2. So I'll put a 2 down here. But now helium, notice, has a fraction here. That means there's more than one isotope that's been averaged out to get this number. So we need to know which isotope of helium. Let's say we're going to work with helium-4. Okay, if I'm working with helium-4, then that means I have 2 protons and how many neutrons? 2 to get a mass of 4. So helium-4, the isotopic symbol or nuclear symbol for the isotope helium-4 looks like that. Okay? But now that's helium, the atom. This is alpha. The difference is this doesn't have any electrons. So if it's made of 2 protons, and what charge do you have on a proton? Positive. And no electrons, because it's coming out of the nucleus. You don't have any electrons in the nucleus. Actually, you do. We'll talk about that next. But the helium, the alpha particle doesn't have any electrons, okay? So this has a 2+ charge. A helium atom has no charge. Oh, sorry. 2+ charge and no charge. Okay? For an alpha particle. Got it? You with me? Well, an alpha particle has 2 protons, which have a plus charge, one each. Neutrons are neutral. No electrons. So I've got 2 particles with a 1+ charge. There's our 2+ charge.
How did you find out the neutrons?
The number of neutrons for the alpha particle? I just told you there are 2 neutrons.
How do you find out?
Because I told you. That's really all there is. I told you. I told you so. Okay. I'm sorry. What?
The alpha particle has
No electrons. No electrons. Yes.
So the 2 numbers beside the little alpha symbol or whatever.
Top numbers.
How you found it, like the
Upper left is the mass. Protons plus neutrons. And there are 2 protons, 2 neutrons, so the mass is 4. The bottom number is the number of protons. And an alpha particle has 2 protons.